Alright, you are welcome to this lesson, and in this video we have been asked to limit this function 1 plus 1 all over n all to the power of n to limit n to infinity. And this might scare you a little, but don't be scared. This is just simple expansion as well. Alright, now you would know that by plugging infinity here it won't just work, but we can apply a simple rule, and that rule is by expanding this function. Now, how do we expand this function? You notice that you have a power of n here, which is kind of unusual and confusing. Now, usually whenever we have a plus b all to the power of 2, we can say a plus b by a plus b, and expand by saying a squared, the first by the first, the first by the second. A times b gives us ab, b by a gives us another ab, and b by b gives us b squared. Now we have a squared. Ab plus ab is twice that value plus b squared, and all is equal to a plus b all squared. Now this is easy and straightforward because you know what you have at the power is 2 and it's simple. But here we have n. What if you have 100 here? What if you have 200? What if you have 5, 6, 7 and 8? It will not be a simple expansion, but there is a tool to solve problem like this. That tool is called Pascal triangle. We call it the Pascal triangle. Now the Pascal triangle let us deal with expansion. Now let us apply that same Pascal method to this same problem and see how it is. I'll even tell you what exactly is going on in this place here. So we have a plus b all to the 2 power. Okay, now what we actually do, when we expand is that we are ascending the first variable and descend the second variable. Now let us see what we mean by this. No, we descend this value here and we ascend this value here. Now, but when you are descending from 2 all the way to 0, you count down from that 2. Now let us go. Now we have a squared and b to the power of 0. Yes, we begin here, plus a is descending while b is ascending all the way to 2. While a is descending from 2 all the way to 0. A2 b0, and we have a1 b1 plus a0 b squared. We will stop here because these two correspond to this power, so we stop. Now when you add up your powers must add up to the power you have here. 2 plus 0 is 2, 1 plus 1 is 2, 0 plus 2 is 2. So we can simplify by saying a squared is a, b0 is 1, so we have a squared, plus a1 is a, b1 is b, plus a0 is 1, b squared is b squared. Now you say you have a squared here, ab here, but you have b squared here. But here you have 2ab. Where is the 2 here? That's where Pascal comes in. The Pascal triangle says that you have to start with 1 and end with 1. You must always start with 1 and end with 1. Now I have begun with 1. Let's start with 1 again. 1 plus 1 will give us 2. Now we end with 1 again. We start with 1 again. 1 again. 1 plus 2 gives us 3. 2 plus 1 gives us 3. You end with 1 again. Start again with 1. 1 plus 3 gives us 4. 3 plus 3 gives us 6. 3 plus 1 gives us 4. You end with 1. Now, all this you are seeing here are for the powers. When you have the power of 2, you use this rule. When you have the power of 3, you use this rule. When you have the power of 4, you use this rule. Now, in this case here, in this equation here, in this question here, we have the power of 2, so we use this rule. All I have to do is just place 1, 2, 1 beside each of them, and they must fit in. If they don't, there is a problem. So 1, 2, 1. So we have 1, 2 and 1. So at the end, this becomes a squared plus 2ab plus b squared, which tallies with what we have here. Now this is the rule of Pascal, and it always works. Now in this case, you notice that what we have here is not a constant integer or a value. What we have here is a variable n. Now, how can we expand this variable? We have to apply the same rule as we applied here in the Pascal, because if we apply the normal expansion, we don't even know where to stop and how to even do this. So let us apply our Pascal method and see what we get. So we have 1 plus 1 all over n to the power of n is equal to, notice what we are doing here, that the first value here decreases from the power all the way to 0, and the second one goes from 0 all the way to that power. So let's do that. The same principle will apply. So we have 1 here, we have 1 here n, and the 1 all over n to 0. And I hope that is clear. Yes, 1n and 1 over n to the 0. So we have again 1n minus 1 all over n to the power of 1 plus 1. You notice that this a is always going down by 1. The same thing applies here. So 1n minus 2 1 all over n by 2 plus 1. So we have 1n minus 3 1 all over n by 3. So let us stop here and at least simplify what we, and this pattern will keep on going like this. So let's simplify this. So we have 1 to the power of n. When you take 1 to the power of any positive integer, we give you 1, and 1 times 1 will give you 1, plus this to give you 1 to the power of 1 is 1, n to the power of 1. So here we have 1 all over n. We have 1 all over n. Now plus here we still give you 1. This will always give you 1. Here we have 1 all over n squared. 1 all over n squared. Now plus here we give you 1. Here gives you 1 all over n cube. 1 all over n cube plus all the way. Now you notice that we are at this point, but we have to also consider our coefficient. Yes, we have to consider our coefficient. We have to. So now by Pascal, all we have to do here is that we have to introduce our coefficient, but we don't even know what to place here. We don't know. So we have to have a constant formula that stands for the coefficient. Now all you have to do at this point here is, you know that this will always be 1. Yes, this will always be 1, and that will give you 0 factorial, because this is not starting at anywhere, so it is 0 factorial. Now this will give you n, and this will give you n into n minus 1 all over 2 factorial. This will give you n into n minus 1 into n minus 2 all over 2 factorial. So now let's go. So we have 1 plus n into 1 all over n plus here we have n into n minus 1 into n minus 1 all over 2, but we have an n squared here, so don't forget n squared. You see that? N squared plus n into n minus 1 into n minus 2 all over 3 factorial n cube. Now this pattern will keep on going. On the next page we have 1 plus 1 all over n to the power of n. Give us what's there? Give us 1 plus n to 1 all over n, and plus n into n minus 1 all over 2 factorial to 1 all over n squared plus n into n minus 1 into n minus 1 into n minus 2 all over 3 factorial into n cube into n cube. Now let's simplify what we have. Now what we have here is this. So we have 1 plus n, we cancel out n here, so we have 1 plus now see this 2 factorial is just 2 and n squared here, so n can cancel out n here, so we have 1 all over 2 into n minus 1 all over n, plus here we have 3 factorial, which is 6, so we have 1 all over 6 into n can cancel n here, so we have n minus 1 and n minus 2 all over n squared, and this will become 1 plus 1 plus 1 all over 2 into, if I divide this by this, I get 1 minus 1 all over n plus 1 all over 6 into, I will be dividing this by, sorry, let me just separate that. We have n minus 1 all over n squared into n minus 2 all over n squared. Yes, all over n squared. So we have 1 plus 1 plus 1 all over 2 into 1 minus 1 all over n into 1 all over n plus 1 all over 6 into n in n is 1 all over n, 1 all over n minus 1 all over n squared, and this gives us 1 all over n minus 2 all over n squared. Now at this point, yeah, this is all equal to the expansion of 1 plus 1 all over n all to the power of n, You notice that n can get very, very large, and we are limiting n to infinity. So now we can apply limit to both sides. So limit as n goes to infinity of this function, 1 plus 1 all over n to the power of n is equal to 1 plus 1 plus 1 all over 2 all the way to 1 minus 1 all over n, all over infinity, plus 1 all over 6 all to 1 all over infinity minus 1 all over infinity squared to 1 over infinity minus 2 over infinity squared. Now you notice that as this man gets very, very large, all this value you are seeing, 1 plus 2 plus that, all this value you are seeing here we approach the value e, we approach the exponential value. So the limit as n goes to infinity of 1 plus 1 all over n, which is a regular pattern we know, is equal to the exponential. If you check it very, very well, after applying your infinity here, you notice that this pattern will keep on going like that, and as n gets to a very, very large value, now if n gets to a very, very large value, all this will approach 1. I assume that all this will approach 1. This approaches 1, this goes to 1, this will go to 1. No matter what, as n approaches a very, very large value, all this will always approach 1. There is no how you do it will almost approaches 1, because how 1 minus a very, very, if this man gets very large, like 1 million, 1 over 1 million is a very, very little value. In 1 is almost nothing. So all this will always approach your exponential value, which we know. And thank you. See you in the next lesson.